Hello, everyone. In this section, we will introduce the characteristics of the ideal diode in Electronics 1. A diode is a two-terminal device. Its two terminals are called the anode and the cathode, as shown in the figure on the right. When the anode voltage is higher than the cathode voltage, that is, when V is greater than 0, the diode is under forward bias, as shown in the upper right figure. In this condition, an ideal diode behaves like a short circuit, as shown in the lower right figure. When the cathode voltage is higher than the anode voltage, that is, when V is less than 0, the diode is under reverse bias. In this condition, an ideal diode behaves like an open circuit, as shown in the figure on the right. From these two bias conditions, forward bias and reverse bias, we can obtain the voltage-current characteristic curve of an ideal diode, as shown in the figure below. Under reverse bias, the equivalent resistance is infinite because the diode is open and no current can flow. Under forward bias, the equivalent resistance is 0 because the diode is short-circuited, so there is no voltage drop across the diode. From the example on the right, we can see that the anode voltage is higher than the cathode voltage. Therefore, the diode is forward biased and is equivalent to a short circuit, so the voltage across the diode is 0 volts. Therefore, the current in the entire current path is 5 volts divided by 5 kiloohms, which equals 1 milliampere. If the diode is connected in the opposite direction, as shown in the lower right figure, the anode voltage is lower than the cathode voltage. Therefore, the diode is reverse biased and is equivalent to an open circuit. Therefore, the current in the entire current path is 0 amperes. Since no current flows through the resistor, there is no voltage drop across the resistor. The cathode voltage of the diode is 5 volts, and the anode voltage is 0 volts. With V defined from anode to cathode, the diode voltage is negative 5 volts. Now, let us introduce one application of an ideal diode, the rectifier. Suppose we have an AC voltage source, VI, with a sinusoidal voltage waveform. This waveform includes both a positive half-cycle and a negative half-cycle, as shown in the diagram. Next, we connect the AC source, VI, to a diode D and a resistor R to form a circuit loop. The voltage across resistor R is defined as the output signal, VO. When the input signal VI is in the positive half-cycle, diode D is forward biased and behaves like a short circuit. In this case, the voltage across resistor R is equal to the input signal VI, so VO equals VI. When the input signal VI is in the negative half-cycle, diode D is reverse biased and behaves like an open circuit. In this case, no current flows through resistor R, so there is no voltage drop across R and VO equals 0. As a result, the output waveform VO contains only the positive polarity portion, as shown in the diagram. A circuit that converts a voltage with both positive and negative polarities into a single polarity voltage is called a rectifier. Similarly, if the direction of the diode is reversed, then during the positive half-cycle of VI, diode D is reverse biased, so the current is 0 and VO equals 0. During the negative half-cycle of VI, diode D is forward biased, so VO follows VI through the short-circuited diode. As a result, the output voltage VO contains only the negative polarity portion. Therefore, in a rectifier, the connection direction of diode D determines the polarity of the final output voltage, as shown in the figure. Besides the rectifier application, we will next introduce another application of an ideal diode, the logic gate. We begin with the OR logic gate. Its operation can be written as Y equals A or B or C, which is also represented by Boolean addition. In digital logic, each bit has only two possible states, 0 and 1. Because this is Boolean logic, even 1 or 1 still gives 1. In simple terms, an OR gate outputs 1 as long as at least one input is 1. The output becomes 0 only when all input bits are 0. The possible input and output combinations are shown in the truth table. In an electrical circuit, the logic values 0 and 1 are represented by a low voltage and a high voltage. A low voltage corresponds to bit 0, and a high voltage corresponds to bit 1, as shown in the table on the right. The OR logic gate can be implemented using the diode circuit shown in the figure. When any one of the input voltages, VA, VB, or VC, is high, the corresponding diode becomes forward biased and conducts. This pulls the output voltage VY to a high level. Only when all three input voltages are low, at 0 volts, does the output voltage remain at the low level of 0 volts. For example, let the low voltage be 0 volts and the high voltage be 5 volts. When VA is at the high level of 5 volts, while the other two inputs are at the low level of 0 volts, the diode connected to the 5-volt input is forward biased and conducts, so the output voltage also becomes high at 5 volts. The diodes connected to the 0-volt inputs are reverse biased and remain open, as shown in the lower right figure. Next, let us introduce another logic gate circuit, the AND gate. Its operation can be written as Y equals A and B and C, which is represented by Boolean multiplication. In simple terms, an AND gate outputs 1 only when all input signals are 1. If any input bit is 0, the output bit becomes 0, as shown in the truth table. The AND logic gate can be implemented using the circuit shown in the figure. When any one of the input voltages, VA, VB, or VC, is low, the corresponding diode becomes forward biased and conducts. This pulls the output voltage VY down to the low level. Only when all three input voltages are high, at 5 volts, does the output voltage stay at the high level of 5 volts. For example, let the low voltage be 0 volts and the high voltage be 5 volts. When all input terminals are at the high level of 5 volts, none of the diodes provides a conducting path to pull the output low. Therefore, the output voltage remains at the high level of 5 volts. If any one of the three input terminals is at the low level of 0 volts, using VC as the example in the figure, the diode connected to that low voltage input becomes forward biased and conducts. This pulls the output voltage down to the low level of 0 volts. The diodes connected to the remaining high voltage inputs are reverse biased and remain open, as shown in the lower right figure. In this section, we introduced the equivalent circuit of an ideal diode under different operating modes, including forward bias and reverse bias. We also extended the discussion to two applications, rectifiers and diode logic gates, including OR and AND gates. This concludes the introduction to the ideal diode. Please look forward to the next lecture. See you next time. Bye-bye.